Peace. Welcome. Here, I'll be trying to explain Hamilton's principle, Lagrangian and Hamiltonian dynamics, which is the 7th chapter of Classical Dynamics of Particles and Systems by Stephen T. Thornton and Jerry B. Marion. I'll be going through the chapter section by section, resolving the examples, and in the end of it, solving some problems too. That being said, let's dive right into it. The first section is an introduction to the chapter. We know from experience that the motion of a particle in an inertial frame of reference can be described by Newton's equation. The net force acting on the particle is equal to the first-time derivative of its momentum. In case you're not familiar with this form of the equation, let me break it down for you. The momentum of a particle is equal to its mass by its velocity. When we take the first derivative of that, the mass is a constant, and the first derivative of the velocity with respect to time is simply the acceleration. Simple stuff, if you don't know it already, which I hope is not the case. Well, now you do. Anyways, Newton's equation works pretty simply if we're dealing with a particle that is not required to move in some complicated manner, and if we're using rectangular coordinates to describe the motion. But to apply the Newtonian procedure, we must know all the forces acting on the particle. Moreover, if the particle is constrained to move on a given surface, then there has to be a force that maintains the particle in contact with the surface. The constraint force, which is the force that maintains the particle in contact with the surface it's moving on. For a particle that moves on a smooth horizontal surface, the force of constraint is simple, it's going to equal negative mg. The weight of the particle is what keeps it on top of that surface while it's moving. But if we look at another example, imagine a bead sliding down a curved surface. The constraint force here is not simple like in the previous one. Here it's unknown, and not constant. It keeps changing as the position changes. Which means here, it's different than here, and different there. To circumvent the difficulties that arise in attempts to apply Newton's equation, an alternative may be developed. The alternative can be contained in Hamilton's principle, and the equations of motion resulting from its application are called Lagrange's equations. If Lagrange's equations are to constitute a proper description of the dynamics of a particle, they must be equivalent to Newton's equations. To be sure, each of the results that can be obtained from Hamilton's principle was first obtained, as were Newton's equations, by the correlation of experimental facts. And in fact, Hamilton's principle has not provided us with any new physical theories, but it has allowed a satisfying unification of many individual theories by a single basic postulate. In view of its wide range of capability, it's not unreasonable to assert that Hamilton's principle is more fundamental than Newton's equations. Therefore, we proceed by first postulating Hamilton's principle. Then obtain Lagrange's equations and show that these are equivalent to Newton's equations. Hamilton's principle is one of the most elegant and far-reaching principles of physical theory. We shall explore it deeper in the coming sections. That's it for the first section. See you in the next. Peace out.